Okay, good morning. I'm Warren James. I'm CTO of Infinity Research LLC. We're a small company that does spacecraft mission design, spacecraft system engineering, and in our spare time we do software development for iOS and OS X. And today I'm going to talk about options for chemical propulsion for delivering CubeSats to the moon. I got interested in this question because I'm always wondering what's the best way to do something, and I was wondering, did chemical propulsion make sense? Was it possible to come up with something that was reasonable for getting spacecraft to the moon using chemical propulsion when you're talking about tiny little CubeSats? Now, our issue facing us isn't so much getting to the moon, but getting to the moon effectively, affordably, and being able to do reasonable amounts of science. Now, I think it is a tribute to the imagination, innovation, and just totally new thinking of the CubeSat community that we have been looking at electric propulsion or solar sails for getting to the moon, combining these with weak stability boundary transfers, and that these technologies, which would traditionally be considered exotic and far out, are in fact in the CubeSat community the conventional approach. So everybody should give themselves a pat on the hand because you've taken something that was exotic and considered hard to do and made it just what everybody assumes you're going to do. You've made it routine. However, as a wise man once said, there ain't no such thing as a free lunch. And these approaches all are small and light and very effective, but they all take between 1 and 2 years to get to the moon. Now that has significant implications for science return, mission reliability, and cost. And let's look at those figures for just a sec. Let's imagine that we're going to fly a mission that's going to spend 6 months orbiting the moon doing science. If you take the slow boat, you spend 18 months getting to the moon, 6 months doing science. You've just spent 2 years flying your mission. On the other hand, if you use chemical propulsion, it can take you 3 to 5 days to get to the moon, and then sitting in Earth, you might have to sit in Earth orbit for about 3 weeks, allowing everything to get lined up, allowing the departure orbit to line up with where the moon's going to be, because if we're hitchhiking to GTO, we can't be guaranteed that we're going to be released in the right place at the right time to go to the moon right now. We might have to wait a few weeks for everything to get lined up. So the chemical propulsion option takes up to a month to get to the moon. Most of that's just hanging out in orbit, doing laps. And then once we get to the moon, we can do a 6-month mission, a 6-month mission, a 6-month mission, and another 6-month mission. In other words, the chemical propulsion system gives you 4 missions in the same time that the conventional approach will get you 1 mission. To put it this way, imagine one group sends out a probe using conventional, again that's lunar cube conventional, propulsion, and another group sends out a mission using chemical propulsion. The folks who went with chemical propulsion get to the moon, do their science in 6 months, then they analyze their data, and they've got their results analyzed and published before the slow transfer even gets to the moon. CubeSat reliability. We all know this sad story. Of the CubeSats that reach orbit, something like 18% suffer infant mortality and never even function. Of the ones that reach orbit, survive being turned on, and then go on to fly their missions, about half of them fail before completing a 6-month mission. So if you've got a reliability of 50% every 6 months, the odds of successfully carrying off a 2-year mission are somewhere between slim, zip, and none. If we assume that we can improve the reliability of our CubeSats so that the infant mortality rate is cut to a quarter of what it has been demonstrated to be, so that the ongoing reliability is a quarter of what it is, so that the failure rate is a quarter of what it has been demonstrated to be. If we fly a 6-month mission, we've got a 19% failure rate by the end of our mission. On the other hand, with those same reliabilities, the conventional approach has a 50% chance of failure. So in order to make sure your long missions have an equal chance of surviving, you're going to have to fly more spacecraft. So science return and reliability dictate that with the conventional CubeSat approach, we're going to have to fly a lot more missions just to ensure that we get something. Now, all of this impacts on cost. We need more spacecraft for the same science return. We need more spacecraft to handle the reliability issues. And with the mission being longer, your mission operations and science team has to be funded for a longer period of time. You can't just hire and fire people for those functions as you need them. You need these people when you design the mission. You need these people during operations. But if you throw in a huge gap between design and operations, you're kind of in a quandary as to what to do with all those people that you needed and will need again. You can't just toss them out the door, which means you've got to pay these people, and that gets expensive. If you're doing this as a university experiment, the long mission time is inconsistent with the residency time of students. Students are at school hopefully for 4 or 5 years. Well, if it's going to take you 3 or 4 years to design a spacecraft and then 2 years to get to where you're going, the students that were there when you started the project, the students who designed and built the spacecraft, are gone. Now, this is bad for the student morale because they did all this work building a spacecraft and then they don't get to be there to eat the cake of flying the mission. Worse, the knowledge that those students have walked out the door when they matriculated. So this raises issues for a university-based system. Also, if each spacecraft has its own propulsion system, this raises the cost of each spacecraft because each one has to build in a propulsion system. Now, for a chemical stage, it will be shown to be best because of scaling considerations if one chemical stage carries a bunch of CubeSats at one time. Now, I will note that a chemical stage is going to be heavier, bigger and heavier than the electric systems that we've looked at. And if you've got a customer that says, I'll fly you if you're a 6U CubeSat, and if you're not, I won't, then you can't use this option. In which case, find a better customer, find a better client. Because there are a number of ways to get into space that don't require dealing with a client that dictates the size of your spacecraft. Chemical propulsion option. Let's imagine a stage that can carry our lunar cubes. There are many, many options, and I don't have time to go through all of them. I'm just going to highlight a couple and then look at one in detail, and if I've got time, I've got slides for another one. But we've got the options. Monoprop hypervols. They're simple. They've got just one tank, a little bit of plumbing, no ignition system, wonderful virtues. But they've got the vice of low ISP, so they've got low performance. On the other hand, biprop hypervols are a little less simple. I need 2 tanks, a little bit more plumbing, but they're very simple in terms of ignition. The propellants are generally storable at the temperatures that we're going to be operating at. Unfortunately, the propellants are poisonous. So that's an issue, but it's an issue we've been working with for the last 50 years. We know how to deal with that. On the other hand, and this is the option that I thought, when I started this is the option I thought was just going to be the best thing since sliced bread. And that is, why don't we launch our stage dry? Don't put any propellant in it. Now, this gives us an advantage. We're not carrying explosive propellants in this stage that's attached to the launch vehicle, so that ought to make the launch vehicle company really comfortable. And then, all launch vehicles carry reserve propellant. You've got to have flight performance reserve to ensure that you reach your target. If you've done a good job, on average, you reach orbit with about half your reserve propellant unused. On a good day, you didn't touch any of it. And on a bad day, you reach orbit as that last drop of fuel goes into the engine. But on average, half of the reserve propellant is available. And that half of the reserve propellant from an upper stage is a lot of propellant for a vehicle of the size we're going to be talking about. Now, there are two options here. One would be to use LOX hydrocarbons. LOX is a cryogen, but not hard to deal with. But the problem is there's only one launch vehicle that we might be using that uses LOX hydrocarbon in its upper stage, and that's the Falcon. The more likely candidate would be LOX hydrogen. Really good ISP, but it's a hard cryogen, and it's a very low density fuel, so the tanks get really big. In terms of doing lunar missions, the relevant delta V's here are 680 meters per second to depart from a GTO periaps. This is based on work that I did on CEV, CER, and a whole bunch of other lunar missions. And this delta V from LEO, 3,100 meters per second, is sufficient to guarantee that you can make a lunar transfer on the worst day of the worst month in the 18-year lunar cycle. So if I'm carrying, if I do that, I can get to the moon pretty much any time. Now, when I arrive at the moon, 1,100 meters per second is sufficient to insert me into a low lunar orbit. Now, I think there was some concern the other day about what inclination might I go into. You know, am I going to go into a polar or equatorial? The answer to that is real simple. I can put you in any inclination. Because what we can do is, as we're approaching the moon, we can rotate the orbit plane around the V infinity vector, and it's literally single-digit meter per second delta V to rotate the V infinity vector to get any desired inclination at the moon. It turns out to be a very easy problem to solve. Coming in on lunar capture. You actually, as you're approaching, what's going on here? What's going on here is I'm far away from the moon, I'm not moving really fast, and rotating the velocity vector depends on what my velocity is, and if I'm just kind of slowly moving along, it takes almost no delta V to spin that vector any way I want. Now I also, though, have thrown in a design reserve of 170 meters per second just to accommodate other stuff. So, the chemical system is designed to generate 1,950 meters per second. Oh, this is the old one. This is not the right one. This was the versions. This was the earlier version. I sent the revised one. I thought it got in.
I thought it got in too. So.
Okay. Yes, please. That has some revisions. Sorry, no, that's okay. While you're doing that, I'll just go ahead and, okay. I'll go ahead and do that, and I'll just talk because I know what's on the slide. The biprop hypergol was a system that I thought might or might not work. Turns out it works really well. The whole thing behind the biprop hypergol is I'm delivering 120 kilograms of 9U CubeSats to low lunar orbit. So that's 6 9U CubeSats with a 20 kilogram per CubeSat allocation.
Or 9 6U CubeSats.
Or you can slice and dice it any way you like. It should say Rev 2, I believe.
I can send it remote control. I'm going to try to do that.
Okay, and I'll keep talking based on this. Now, we designed this stage using CubeSat hardware for all the major spacecraft subsystems, comm, radio, ACS, batteries, all that stuff. We just use CubeSat hardware. Why should I spend my time designing a radio when I can just go buy one? So we use CubeSat hardware. We're using storable biprops, monomethylhydrazine and nitrogen tetroxide. We size the system for an acceleration of 2 meters per second squared. And you'll notice this typo proves one of my laws of presentations. No presentation is complete unless there's a typo that isn't discovered until you're in front of an audience. What can I say? But we designed the system for 2 meters per second acceleration because that minimizes our finite burn losses during these major burns. ACS thrusters are used for TVC during the main propulsion burns. The ACS thrusters are sized so that during the main propulsion burn, we operate them in a pulsed mode for attitude control. Now, we use CubeSat components and all this other stuff. When I get to the moon, oh,
I can load it up right now. You want me to do that?
yes, please, because
I thought it was.
I've got a.
I thought it was. I'll put it on there right now.
Okay.
Okay.
We built this using CubeSat components,
You'll be
and
the
so
last-
once
you'll
we
be the
reach
last
the moon and we're in orbit around the moon,
Is that okay?
and it only took us a month at most, I've got a CubeSat. So the stage becomes a CubeSat once it reaches the moon, and so I also have added on a weight and volume allocation equivalent to a 4U CubeSat that's permanently attached to the stage so that when I get to the moon, somebody has a 4U CubeSat for doing lunar science. And we don't count that CubeSat payload in the 120 kilograms of payload that I'm delivering to the moon. So I'm actually delivering 6 big CubeSats and 1 medium-sized CubeSat. Launch vehicle integration. Where am I going to put this thing? There are a number of systems that we can use for carrying a chemical stage, and something like this, the integrated payload carrier, which is based on the ESPA ring, is a great option. It has an internal diameter of just under 1.4 meters, and it's about 2 meters long, and you can put 910 kilograms inside of it. So that gives me a volume that I have to fit within. If I can fit within that constraint, we're golden. Now, this system didn't necessarily allow for the integration of a vehicle with hypergolic propellant, so that does remain an open issue that we'll have to work with the launch vehicle provider and other people. Now, this system was designed for use on the EELV, but we could also apply it to Falcons and other things. Let's look at sizing. Got the other slides?
On the smart sheet, and I'm sure, and Speed's gonna, as soon as he gets them on his system, he's going to bring them up.
Okay,
in front
that's
of the room.
good.
I'm sorry about that.
No, that's fine. The only thing is I've got an illustration of the stage that's on the
Okay.
revised version. Let's talk about sizing for a moment. I put a 30% margin on the spacecraft hardware and a 30% margin on the tank volumes. 30% margin at this stage of the game is reasonable, especially since a lot of the hardware we know what it weighs. But the 30% margin on the tank volumes means that if we need a little more performance, we can get it by putting in more propellant. Tank weights themselves, and that's the real challenge, because tanks don't scale well, and tanks at this size are kind of wonky. But I'm using an empirical set of relations from SMAD based on ACS tanks that have been flight qualified and flown. So the tank weights are believable because they're based on existing flown hardware. When we go through the sizing exercise, the stage weighs 190 kilograms. We need 250 kilograms of propellant in order to fly the mission. Our hydrazine tank is 60 centimeters in diameter, and the oxidizer tank is 66 centimeters in diameter. The whole stack is just about 2 meters when all is said and done. In other words, that stage and its payload is a little taller than me and a little wider than me. So it's not all that big. Thank you. Okay, yeah. This is a conceptual configuration for this vehicle. I chose to use a wireframe to emphasize that it's a conceptual design as opposed to doing a nicely rendered, texture mapped, and cool CGI illustration. I like to remind myself and everyone else that we're dealing with conceptual designs. Here are the 2 propellant tanks. They're tied together with an aluminum truss. You will note that I've taken out a number of elements for simplicity. I've taken out the cross bracing on the truss. I've taken off thermal blankets and various other things. I've simplified this for illustration. So our oxidizer tank, our fuel tank, pressurant tanks, a 1 kilonewton thruster is sufficient for what we need here. Up here we have ACS thrusters on little booms just to give them the greatest amount of torque. We have one box containing the lunar cubes. This is the dedicated lunar cube that's a part of the stage. And over here we have another CubeSat box containing the spacecraft subsystems. In the middle we have a tank for attitude control propellant. We have fairly large solar panels up here. They seemed large when I was putting them on, but compared to the whole thing, they're not. They're actually we end up getting about 75 watts of power. During cruise, in fact, the solar panels would be folded against the side of the vehicle. The vehicle would be oriented with this long axis normal to the sun line, and then we would go into a barbecue mode just to keep thermal control issues under control. And on top, we have our lunar cubes. That's 6 9U lunar cubes. Launch cost impact. You're gonna think, you look at this thing, it weighs 500 kilograms, and you're comparing it to CubeSats that weigh 20 kilograms, and you've got to imagine that this is going to really, really, really hurt in terms of launch cost. However, remember, on the chemical stage, I'm delivering 6 CubeSats plus 1 dedicated CubeSat. And for the conventional approach, I need multiple missions to get the same amount of data and the same amount of reliability. So when I'm comparing launch costs, the only way to do an apples-to-apples comparison is to compare a single chemical launch with the requisite number of conventional slow boat launches so that I can achieve the same science goal. You know, 1 chemical mission equals at least 4 slow transfers. So you need more launches to get the same results if you're using the long transfer times. So if we look at the launch cost per kilogram to geostationary transfer orbit, currently a SpaceX Falcon 9 Heavy has a price that kind of falls at about $13,000 per kilogram. So if we look at a small chemical stage, we're looking at a little under $1.5 million for launch cost. If we look at, again, a campaign of multiple launches of slow transfer vehicles, it's going to cost you $1.5 million. In fact, the chemical stage costs less for your launch cost because you can do in 1 mission what the other approach requires several missions to do. Now, I will admit that even though the chemical stage is less expensive, the difference is not that great. But the point is, the chemical stage is no more expensive than the alternative. Now, let's a couple more slides, and then we'll be getting toward the end here. Options and contingencies. Remember I said I sized the propellant tanks with 30% free volume. If I fill the tanks up all the way, if I fill the tanks up all the way, I can carry an additional 414 kilograms, an additional 92 kilograms of propellant, or payload rather, sorry. So if I fill the tanks, that's almost 75% of the nominal payload is what I can carry if I just tank everything up all the way. If I keep the payload weight constant and just use that extra propellant for delta V, I get an extra 414 meters per second of delta V. So I've got lots of interesting options. What's really exciting to me is what I can do if I take this stage and just book out of cislunar space. If I take that stage, here's C3 that I can achieve as a function of payload mass. If I take this stage and book out of cislunar space, C3 is in the 20-ish range, take me to Mars. So I can inject something like 200 to 300 kilograms of payload on a Mars transfer orbit. Now that obviously doesn't put you into orbit around Mars, but that's where your electric propulsion could come into play. You could then take that 300 kilogram spacecraft and put it in orbit around Mars. If you want to go to the asteroids, we're down here in the 10-ish low range, and there I could put 400 or 500 kilograms on trajectory for an asteroid. In many ways, though, the most exciting option is launching on a C3-0 trajectory. C3-0 is just an escape trajectory. You depart cislunar space, and when you leave the Earth's sphere of influence, you're in a 1 AU heliocentric orbit, just slowly drifting away from the Earth. I can put between 700 and 1,000 kilograms of payload on a C3-0 trajectory. Now, in the talk earlier today about a low-thrust system doing asteroid missions and things, what could you do with 1,000 kilograms of spacecraft escaped from the Earth, and now you use the electric system to trim your orbit to go to the asteroid and do other things? We would not be talking about, you know, a 20 kilogram or a 10 kilogram science payload at an asteroid. We'd be talking about a science payload that's as big as anything NASA's flown for most any other mission. This takes us out of the realm of being, you know, the little small stepchildren and being the big players. So combining this with electric propulsion for interplanetary missions gets really exciting because we can fly heavy payloads long distances easily. Now, okay, I know I'm running really long, so I'm just going to step over these real quickly and just say that when I did the analysis for the stage with scavenged propellant, I thought that was going to be a big winner. Turns out the hydrogen tanks are so much bigger than the hypergol tanks that there was literally no benefit from the hydrogen. And you've got a lot of problems that you will have to address: cooling down the tanks, for fueling them, when and how to transfer the propellant, and all the other things. But basically, my hypergol stage weighed 560 kilograms, ready to go to the party. The hydrogen stage, dressed and ready to go to the dance, weighed 570 kilograms. So for missions of this size and delta V, there doesn't appear to be any real big advantage to the scavenged propellant hydrogen vehicle. Closing comments. Small chemical stage can carry multiple CubeSats to the moon faster, cheaper, and more reliably than the conventional approach, the very imaginative conventional approach that the CubeSat community has been looking at. It's more cost-effective than those other systems. We get no significant difference in launch cost. We get a shorter transfer time, so we save a lot of money there, and we also get to go out, do something, publish it, and move on to the next mission. We can reduce the cost of the Lunar Cube hardware because we can take a lot of subsystems out of the Lunar Cube because you don't necessarily need them if you're going to be delivered to low lunar orbit. We can be carried within weight and volume constraints of existing rideshare options, and I think in the next 5 or 10 years, there's going to be a lot of rideshare options when SpaceX starts flying the Falcon Heavy, because it's got a lot of capability, and compared to its capability, we're just a little blip on the charts. I will also note that other mission design studies that I have done in V-Infinity Research show that we can take the stage and use it for landing significant payloads on the lunar surface, and do so without making major redesigns to the system. We can fly very exciting asteroid, Mars, and other missions. This really does open the solar system to the CubeSat community. Thank you, and I apologize for running long.
Yeah, what I'd like